So we can go ahead and launch the emission. What you see is that the points are launched a little distance away from the surface. Lorentz is using the emission law. It has a small distance offset calculated in, and it's using that to produce the initial behavior. So the initial gap here may look disconcerting, but it is actually irrelevant. The gap can be made, in this case, as large or as small as you wish. In the case of a real model, experience shows that so long as the gap is less than approximately 10% of the emitter length, it is actually unimportant. That is, you will get the same physical prediction for gaps within that size range. So you saw that it ran the emission and repeatedly calculated the electric field. You can look at the results in the message area within Lorentz to see the repeated calculation of the field and the recalculation of the current. You can also look at a graph that's automatically produced that gives you the same information. And if we make the font larger here, what you see is that before there was any space charge present, there was a very large amount of current, relatively speaking, almost at 300 amps. That is more current than can pass through this device according to the Child's law prediction. So the amount of charge associated with that dumped in causes the next iteration to deposit too little charge. And then as you go from iteration to iteration, the oscillations around the correct value become smaller and smaller. If you look at iteration number versus current, you will see that we start at almost negative 300 amps and we end up at 103 amps as predicted by the spreadsheet. Again, the spreadsheet predicted 103.1. We observe 103.01, which is certainly within the 0.1% accuracy specified when the problem was set up. The last thing that we can look at here for this quick demonstration is to look at the actual field results, which will now have been affected by the presence of the charge. And what you see here is that the electric field is very small at the emitter and then rises away from the emitter. This is because you have the same current in the rays throughout the entire length of the trajectory, but the rays are moving more slowly near the emission point. And in fact, the criteria where you pinch off the beam is when there is enough charge present that the field is exactly zero right at the emission point. And as the rays are traveling more quickly, the charge in the beam is covering more space in the same amount of time, and therefore the charge density becomes lower, resulting in a higher electric field at those points.